Thank you very much. Thank you very much for the invitation, Louise, Elisa, Joseph. It's a big pleasure, and I'm happy that it takes place this year. It's online, but it's very nice that it happens right now. So I will start with the 10 hours lectures, and first today is 4 hours, and tomorrow is 4 hours, and on Thursday I have 2 more hours. And today I will talk about pricing and calibration, sorry, with neural networks in finance. So the 10 hours in total, I'm thinking of building it up as follows. So we start with option basics today, 2 hours to get acquainted with the notation and to get familiar. Then in the next 2 hours this afternoon, the idea is to talk about European option pricing, the cost method, and also neural networks, how we can use neural networks. Tomorrow morning, I'll start with American option pricing, say something about PDEs and the cost method for American options in this case, and also about Bermudan options and this SGBM method, the stochastic grid bundling method. And tomorrow we finish off with dynamic optimal asset allocation, which is in the same flavor as early exercise options or options in which you have to take decisions. So it is a decision-making process essentially. And then on Thursday, I'll talk about the 7-league scheme, which is taking big time steps in Monte Carlo simulations with the help of neural networks. And also CVA, Credit Valuation Adjustment, and also how we use the neural networks over there. And of course, needless to say that this is joint work with many of my PhD students and co-workers for many years. So it is an overview of some of the work that we did. All right, today, the first lectures, I will talk about option pricing, say something about the mathematical framework, but I'll be brief about that. I'll say in some more detail, I will discuss the Heston model, stochastic volatility model. And then in the second part, I will say, no, also in the first part, I will do the characteristic function, explain how we come up with the characteristic function for a couple of examples. And then in the afternoon, it will be the cost method for European option pricing, and also pricing and parameter calibration with the help of neural networks. And there we use a neural network that we have developed, and that's called CAN, Calibration Neural Network. All right, we start rather basic. So this is the first lectures, they are joint work with PhD students, formerly Fang Fang, Shuai-Cheng Liu, and also with Sander Boté, who's a professor in Amsterdam, Anastasia Borovic, who is a postdoc in England, and Lech Grzelak, who is my former PhD student, but now a quant in Rabobank, and as a matter of fact, also a co-worker in Utrecht University. Okay, we start rather basic. Suppose, just to set the scene, suppose you have stocks of a company XYZ, and you'd like to have cash in 2 years, for example, to buy a house. And you'd like to have at least K euros for your stocks, but you're afraid that the stocks may drop in the coming years. So how to make sure that you will receive K euros, at least K euros at that time? That is, of course, a possibility is you can buy some sort of insurance against the falling stock prices, and that is the standard version of the put option. And so the put option gives you the right to sell stocks at a future time point. And then what are the risks involved? Well, of course, the uncertainty is in the stock price. You don't know the development of the stock price in the future. So the put option gives you the right to sell stocks in the future at a previously agreed price. So we are now here, we have one of my favorite graphs. This is the time axis here. Here you see the time axis appearing, and in the time axis, we have the capital T, final time capital T. And here we have the stock axis, and we are now at stock value as 0. And when the stock goes up and develops very well, then there's no need to sell the stocks for K, of course, because in the market, we can sell them for a higher price, right? We can sell them in the market for ST. So in this range, the put option is worth nothing. Whereas in this range, when the stock goes down and the development is not good, then you take your option, you exercise your option and you sell your stocks for K instead of S of T. So in this range here, the value is K minus S of the option. And in the range here, the value is 0. So we know the value of the option at final time. The value of the option is denoted by little v in this case. At final time, capital T. And for the stock value, ST, it is the maximum of K minus ST and 0. So we know it at final time, and one of the purposes is to get to the option value or the fair value of the option at time 0. And then, of course, there is a whole range of, let me see, I'll do it like this, yeah. There is a whole development in terms of introduction to financial mathematics that tells you essentially that you can get the option by solving the option value by solving the so-called Black-Scholes equation, dv dt, plus 1/2 sigma square s squared, the second derivative of v with respect to s, plus rs dv ds minus rv is equal to 0. So with this, we can compute the whole option surface, in fact. So here, if we look at our picture here, we have the time axis from 0 to capital T. We have the stock axis here. And what we see is that at final time, we have the payoff of the put, the maximum of K minus S and 0, that is this one. And we see the development, so we have essentially the stock values for any point in time and any stock value. We know the corresponding option value. We have V for all S and for all T values. And particularly we have V for the value S0, T0, which is here, right? That is where we have it. But the white line here represents the stock value in the future. And the stock value, any value the stock may take under the model that we are dealing with here, we would know the option, the corresponding option value. Of course, there are important assumptions here. First of all, one of the assumptions is that the stock price is modeled by geometric Brownian motion. That's a very important assumption. So the stock price is capital S. And geometric Brownian motion, the corresponding dynamics, dst, is equal to rs dt plus sigma s d omega t. So I denote my Brownian increment as omega. So again, this is, well, you have the famous books by Shreve and other books, Oxendahl, and you can get to the Black-Scholes equation. So that is all very nice. However, in the real world, if we look at market data, then we see that the Black-Scholes model is not always accurate. So essentially, if we have this, and we have an analytic solution for the Black-Scholes equation, and we know a lot, suppose we have the option value from the market, we know the stock value now as 0, we know something about our risk-free rate, which is very small at present time. We know the strike price, so we know a lot. The only thing that we do not know is the development of the volatility in the future. The sigma in the future, we don't know. We are now at time 0, and we need to say something about the interest rate in the future, but that's not so serious in this case. And we have to say something about the volatility in the future. And typically in the Black-Scholes world, we say sigma is a constant, either a constant or a deterministic function in time. Now, if we look at market prices, And we look at, if we include the market prices in our formula, then basically the financial option data suggests that the Black-Scholes model is not accurate. If we look at a whole bunch of option values with different strikes and different times to maturity, capital T or T, capital T minus T, if we look at those, then we see that the volatility is not constant. Moreover, it is not easy to predict how the volatility looks. If we look at this, graph here, we see the implied volatility, the volatility that originates from the Black-Scholes model. So which volatility would we take in the Black-Scholes model to get the corresponding market price? And what we see is here we have the time to maturity. So for short time, we see something like a smile, because here we have log moneyness, log S over K. So for different K, S over K, we see something like a smile appearing, and in time this flattens out. So we have, for longer times, we have a flat volatility, but this is the shape of the volatility that we would need to insert in the Black-Scholes model in order to get the market prices. And here we see some hump, and here we see a steep smile, and it flattens. It is basically not a deterministic function. It's not a known time-dependent function. Volatility is not constant in the real world, and we don't know exactly how it looks, and it looks differently for every stock. So again, implied volatility. Famous quant, Rebonato, once said, it's the wrong number in the wrong formula to get the right price. And so it is the volatility, therefore it's a number, it's the volatility that we should include in the Black-Scholes formula, which is not the accurate formula for the market in many cases, to get the right price, to get the market price. So typically, again, let me briefly explain it. We have a closed form solution, the Black-Scholes equation, which depends on sigma R capital T, K, the strike price, and S0. That gives us the option value with the Black-Scholes formula. And we know everything. We know V from the market, we know R, we know capital T, K, and S0, and we only don't know sigma. We only know that it's that the Black-Scholes price is monotonically increasing in sigma. So we can look at we can try to extract sigma from this equation. So it's an implicit equation, it's a nonlinear equation, and we look at the volatility that is implied from the market that gives us the Black-Scholes price. So it's the wrong formula, the Black-Scholes formula. Implied volatility is the wrong number. It doesn't really tell us something. The only thing it tells us is that it is some sort of measure of the uncertainty in the future market. So therefore, wrong number in the wrong formula, but we get the right price. We get the market price of the option. Now, how do we solve it? Well, there are many ways, but the most commonly known is, well, we will use root finding techniques. And we will solve the equation, the Black-Scholes formula, with our unknown minus the market value of the option is equal to 0. And typically we all know the Newton-Raphson iteration, right? And it is well known. But in our case, we will later, in the end of today's talk, I will show you that there is some benefit in using a very, very robust root finding technique, which is Brandt's iteration. Well, Newton-Raphson, we know, right? It is like this. The new iterant for the volatility, sigma at iteration k plus 1, sigma implied, the implied volatility at iteration k plus 1 is equal to the implied volatility at iteration k minus the value that we have found of the option at iteration k minus the market option value divided by G prime, and G prime is dV d sigma, and dV d sigma is known as vega, the option vega. And this is a good method. It works often. However, sometimes Newton-Raphson may fail to converge, and that is either when the vega is extremely small. When vega is small, you can imagine you divide by 0 and it may not go right, or when the convergence stalls. And we do have extremely small vegas when we are deep in the money and deep out of the money. So here we have vega against the moneyness, log S over K, or S over K itself here. And here we have the range at the money. So S is almost equal to K. Here we have in the money, here we have out of the money, and we look at vega, and we see that vega deep in the money and deep out of the money, vega is almost 0. So we may divide by a very small number. And also here we see we have the option price versus the volatility for different values of the moneyness. And we see also here that sometimes the option price, so the vega dV, the sigma is almost 0. So, and also here it is almost 0. So the vega, the option vega, G prime in this equation becomes close to 0 in certain regions of deep in the money and deep out of the money options. Now, what is Brand's iteration? It's a very classical iteration. It is, in fact, also the basis for F-min-con in MATLAB. It's derivative-free, it's robust and efficient. It combines bisection, inverse quadratic interpolation, and the secant method. Yeah. So the first part that one uses is in order to determine a next iterand in the nonlinear iteration, use an inverse quadratic interpolation with 3 points. Based on 3 points. And that often works fine. Yeah, it often works fine. However, when 2 consecutive approximations are identical, so when we have something like sigma k equal to sigma k plus 1, then it may not work fine, but then automatically the quadratic interpolation is replaced by the secant method. So basically this method always makes sure that it converges for any parameter set and for any start value, for any parameter set, this converges, and it is rather efficient still. As compared to the bisection method, it's rather efficient. Well, why is this useful? Well, later, when we do neural networks, we can come up with a number of a very, very different number of combinations of parameters sigma, or combinations of parameters r, t, k as 0, and it should always converge. Yeah, during training of a neural network, it should always converge. You cannot have that sometimes it doesn't converge in that case. So we will see later in the afternoon, we will see that such robust techniques are very important in order to guarantee that a neural network training stage works fine. Okay, so concluding this first part, the Black-Scholes model and its notion of hedging options by stocks and money, it forms the foundation of modern finance, for sure. However, empirical studies of the financial time series, they have shown that the normality assumption for asset returns cannot capture the heavy tails and the asymmetries that are generally also present in log asset returns in practice. And moreover, the volatility, which is supposed to be a known deterministic function of time in the Black-Scholes case, that is inconsistent with the numerical inversion of the Black-Scholes equation based on market prices of options with different strikes and a fixed maturity, because these produce the so-called implied volatility skew or the implied volatility smile, and we cannot model that with the Black-Scholes equation. So we need to look for other models. Typical models that have been developed are the local volatility model, the model of stochastic volatility, which we will focus on here, and also models with jumps. They better fit the market data and they can incorporate these smile effects. So that is important. However, with these more advanced models, also we need more advanced numerical techniques. Because as I mentioned, we have for Black-Scholes, in the Black-Scholes world, we have an analytic solution. However, we do not have that anymore in the stochastic volatility model or in models with jumps in general. So therefore, we need to work on our numerical techniques. The Heston model, let me also briefly explain that to you. The Heston model, it consists of two stochastic processes, one for the stock S and one for the variance nu t. And under the so-called risk neutral measure, the system looks as follows. We have an equation for the stock, dst is equal to rs dt plus the square root of nu s d omega related to the stock price process. And then we have an SDE for the variance, d nu t is equal to kappa nu bar minus nu t dt plus gamma, the square root of nu t d omega nu. So the second Brownian motion. And so we see a number of changes here. In the Black-Scholes world, we had here a constant, sigma. So the square root of nu is replacing the sigma. So, and that makes sense because nu is the variance. The square root of nu is like the standard deviation, and the volatility is a measure of the standard deviation. That is one thing. However, we see more parameters appearing. We see a nu bar, we see a kappa, we see a gamma. There will be a correlation between the two Brownian motions, and we see the risk-free rate R appearing. So where in the Black-Scholes world, we only had the implied volatility, now we have many more parameters. And these parameters should be fitted. They should be calibrated to the market. Yeah. So let's look in some more detail at these parameters. So we have the correlation between the two Brownian motions, that is rho x nu. So d omega nu d omega x is equal to rho x nu dt. We have parameters kappa, non-negative, nu, non-negative, gamma, positive, and they are called. So if we look at this second equation here, we recognize a CIR process, Cox-Ingersoll-Ross, Cox-Ingersoll-Ross process. It has a mean reverting property, and it is essentially a square root process. It cannot go negative. That is good because a variance cannot go negative. The mean reversion has an economic interpretation. We typically know from economic features that when the volatility is high or when the uncertainty in the market is high, there are market mechanisms that take this essentially back to its mean. And when the uncertainty in the market is relatively low, when the volatility is low, there are other forces that bring it back to its mean, so bring it up. And that's a mean reverting feature. Then kappa is the so-called speed of mean reversion. Nu bar is the long-term mean of the variance process. And gamma is called the volatility of volatility. It is the uncertainty parameter in the uncertain process, essentially. Yes, so here we have it again. R is the rate of risk-free rate of return. Nu bar is the long vol, as they call it in financial terminology. It's the long run average price volatility. or variance. So in limit t to infinity, the expected value of the variance is nu bar. It will converge to nu bar. Kappa is the rate at which the variance reverts back to the long run, the long vol. And gamma is vol, the volatility of the volatility. It determines the variance of nu. Well, we know a lot about this model, and I will not go in detail. I have provided you a lot of slides with a lot of details, and I will skip over many of these details because of time reasons, and it's just for you to read it. But what we know for such a model, what we know for the nu process, for a CIR process, we know its distribution. It is distributed according to, so variance nu is distributed according to C bar, which is a function, times the non-central chi-squared random variable, with two parameters, essentially. So chi kwadraat, chi-squared. Two parameters, d bar, the degrees of freedom parameter, and lambda bar, which is known as the non-centrality parameter. So in fact, nu is distributed as the function c bar times chi-squared. And we know c bar, d bar, and lambda bar, and they are based on the parameters in our problem formulation, on kappa, on nu, on rho, and on gamma. In detail, C bar is related to kappa, gamma, and kappa again. D bar is related to kappa, nu, and gamma. And lambda bar, the function, is related to nu zero, the initial variance, to kappa, to gamma square, and in this way. Yeah. An important notion is that we are dealing with a square root process for the variance, and it precludes negative values for nu. So when nu reaches zero, it will subsequently become positive. And it is well known that it is the so-called Vela condition, 2 kappa nu bar greater equal to gamma square. That guarantees that nu stays positive. Otherwise, when 2 kappa nu bar is less than gamma square, then the Vela condition is not satisfied and the variance process may reach zero. But when it reaches zero, subsequently it gets non-negative again. It gets positive again, sorry. So these are the two models that we will be dealing with in this morning's and the afternoon session. We have the Black-Scholes equation and the Black-Scholes stock model. DST is RST dt plus the square root of nu st d omega. And the square root of nu is in fact our sigma from before. And we have the Heston model, considering stochastic volatility. The volatility is stochastic. dst is equal to rst dt plus the square root of nu t, which is now an STE, a time-dependent random process, st d omega s or d omega x, and an STE, a mean reverting CIR process for
Yes, hi. I can't hear Cornelis. Luis, are you there? Cornelis, we cannot hear you.
Yeah, yes.
Hi.
Hi, Cornelis.
I'm going to write him an email.
No,
Okay.
no.
Can you hear me now?
Now
Yes.
we can hear you. Yeah, yeah.
Now, yes.
Okay, I'm sorry. I'm sorry for this inconvenience. So we have the two models that we are dealing with, the Black-Scholes model and the Heston model, and we have 5 parameters that are unknown to us here. It is kappa, nu bar, gamma, rho, and also the initial variance nu zero. They need to be found in the market. Okay, so let's see what these parameters do. Of course, as I mentioned, in the Black-Scholes world, we have the variance sigma square, it's constant. In the Heston model, it's driven by this mean reverting stochastic process for nu. And I want to show you each of these parameters, kappa, nu bar, gamma, and rho, they have a specific effect on this so-called implied volatility curve. And I want to show you these specific effects. So to analyze this, to analyze the effect of the parameters numerically, we do an example. We use the following set of reference parameters. We use rho being 0, kappa 1, gamma 0.1, nu bar 0.05, and nu 0, 0.05. And now we will change each of the parameters, keeping the other ones fixed. And we look at the impact on the implied volatility surface. Yeah. So, and we do that, we compute these implied volatilities with the Newton-Raphson algorithm here. So the first thing we do is we vary correlation rho, and we vary the volatility of volatility parameter gamma. And what we see it in this picture here. What we see is that when rho changes, rho is 0%, so with correlation 0%, we have a straight line. And what we see here is the strike price K here, the strike price K. And here we see the implied volatility. And the straight line is for rho 0. And then rho gets more and more negative. Minus 25%, minus 50%, minus 75%, minus 90%. And each time we see the curve steepening. Yeah, we get a skew. And here we have range from 18% volatility to 26%. And indeed, it is well known that the correlation parameter should be negative, because when the uncertainty goes up, when the volatility goes up, stock prices go down. So therefore, we have negative correlation, and we see that the rho has an impact on the skew, the so-called skew. A bigger, smaller correlation parameter gives us more skew. And here we see the impact of gamma. Again, we have K, strike price K on the horizontal axis, and we have implied volatility on the vertical axis. And the straight line here, that is gamma 0.1. And then we will increase gamma 0.3, 0.5, 0.7, 0.9. And what we see happening is that we see a smile appearing. Yeah, a volatility smile. And for gamma 0.9, we see a so-called steep smile. So with the parameter gamma, in the primary effect with parameter gamma, we can work on the skew that we observe in the market. With the curvature and the smile that we observe in the market. For that, we have parameter gamma, and with parameter rho, we can work on the skew that we observe in the market. Now let's look at 2 other parameters. We have the speed of mean reversion, kappa, and we have nu bar, which is the long-term mean. And essentially what we say here is the speed of mean reversion kappa has a limited effect on the implied volatility smile or skew. Because we see kappa is changing here from 0.1 to 2. But if we look at the axis here, we see it's only moderately changing from 22% implied volatility to 24. It's rather mild, and we change kappa drastically. So there's not much happening with kappa here. However, kappa determines the speed at which the variance or the volatility reverts back to the mean. Yeah, so for a big kappa, kappa 2, we have a very fast convergence to the mean variance, and because here we have the time to maturity on the horizontal axis, and for a very small kappa, we have a very slow convergence to the mean. So this is another feature that is captured by kappa. And of course, the mean is 5% here. The mean is, so the square root of nu is then 22%, and that is the 22 that we observe over here. So basically, kappa and nu bar, they have another effect. They have not so much effect on the implied volatility surface, but they deal with other features in the market. Now, finally, nu zero and nu zero is, of course, the starting variance, the initial variance, and nu bar is the variance level, the long-term variance. And they have a similar effect on the implied volatility curve. So the effect combination is with the value of kappa, which controls the speed. And it is, of course, the start of the implied volatility surface. Here we have the strike value again, K, and here we have the implied volatility, and we vary the long-term mean, and we see that the long-term mean then has some effect on the level at which we start. And the same here we have time to maturity, and V0, we have the starting value that impacts the implied volatility at the money. So we know what it can do, but the most important is, of course, that with this rho and this gamma, we can in fact generate an implied volatility skew or an implied volatility smile. Now, how does it work in banks? That is what I wanted to show you in order to talk about the numerical methods. Well, if we have financial engineering in practice, then a pricing approach is the following. First of all, we start with a financial product, as a typical difficult financial product, because the market asks for it, right? So it is something to hedge or something to ensure some cash flows, maybe something with foreign countries or something with age, a pension product, whatever. It is a difficult product. Then the first thing one has to do mathematically is one has to model the asset price involved. It can be stock, it can be interest rate, it can be foreign exchange. Something is happening. And there we have the SDEs, the stochastic differential equations. Well, these SDEs have their open parameters. Think of our Heston SDE, it has 5 open parameters. So we need to calibrate the model to market data. We need to calibrate, we need to fit the model to the market. And we do that typically with very basic products. We do that with basic products like with very basic option products, European options. And calibration means that we need to iterate and improve the value. We look at the difference between market data and model data, and we may need to do that with 10,000 iterations or something like that. In other words, there's numerics involved and there's optimization involved, and it needs to be done as fast as possible. This is step 3 here is something like speed. We need something that has high efficiency. Well, after step 3, we have essentially fitted our SDEs. We have our SDEs, we have the values for the model parameters, and then we return to step 1. We model the product that we're dealing with a mathematical model, and in the end, we will get a PDE or an integral. Yeah, so we will get a PDE or an integral. We have a difficult payoff. We have maybe multiple asset classes. So here we have an involved PDE and an involved integral. And that needs to be solved. That needs to be priced. However, that needs not be priced 10,000 times. It's only maybe once a week or twice a week that this product is being sold. So this product is only sold several times. So computing the price may take some time. It doesn't really matter that it takes a bit longer. However, it needs to be robust. So in this case, we typically either deal with PDE techniques or with Monte Carlo, but it needs to be priced in a robust way. Then step 6 is, of course, we need to, well, for example, in certain products, we need to understand the risk related to the default of the counterparty. So we need to assess the risk that the counterparty can go in default. And that is again an SDE and some optimization. And we need to understand this and to remove the risk by means of a hedge strategy. So this is also some stochastic analysis, optimization, and some numerical techniques. So essentially, you see 2 steps where numerics come in, step 3 and step 5. And step 3 needs to be done as fast as possible. And step 5 can take some time, but it needs to be robust. So in step 3, we have the speed, because we need to do this 10,000 times to fit the model parameters to the market parameters or to the market prices. And this one, well, it needs to be, it cannot compute too long, of course, but it needs to be done in a rigorous way. And here the product is really difficult that we need to solve. And here the product is maybe relatively standard. So in our methodology, we have to calibrate 5 parameters for the Heston model. And for the Heston model, again, after a course on computational finance, we may need to solve this PDE, dVdt plus RS dVds plus kappa nu bar minus nu dVd nu plus 1/2 nu s squared, the second derivative of v with respect to s, plus r gamma s nu, the mixed derivative of v with respect to s and nu, plus a term with the second derivative with respect to nu, minus rv. So this PDE is much more difficult to solve. It may take some time to solve this, in fact. And we have a payoff. When we are dealing with a simple European option, we have the maximum of s minus k and 0. When we are dealing with a simple put option, we have the maximum of k minus s and 0. Well, I'd like to do 2 more slides, if you allow me, because then we have the basis to get to numerics. One slide is the following. So here you see the Feynman-Cutts theorem. So consider the problem in case of the Black-Scholes equation. We have the Black-Scholes PDE and a final condition. Yes. And then we know from Feynman-Cutts theorem that the solution to this PDE is in fact has a stochastic interpretation. The solution is e to the power minus RT minus t times the expectation under the risk neutral measure Q of the final condition V at capital T as T given the filtration at T. And where under the Q measure S, our S satisfies the following SDEs, SDE, DST is equal to RS dt plus sigma S d omega. And this is interesting, and we have the same for the Heston PDE and SDE and for others. Similar relations between the PDE formulation and the stochastic interpretation, they hold for other SDEs and PDEs. And this opens up the way, this opens for us the way to do numerics, right? If we do this, we do finite differences or maybe finite elements and we solve the PDE. And if we do this, the discounted expectation of the payoff, expected value of the payoff, then here we may recognize, well, an expectation is an integral. So we may recognize quadrature techniques and we may recognize Monte Carlo techniques. So this Feynman-Cutch connects the PDE formulation with the stochastic approximation. And again, if we have an expected value under the Q measure, that is nothing but quadrature. So V, the option value at T0 S0, is equal to the discount, the integral over R of the final condition V at capital T, times the transitional probability density function or the probability density function, that ST, given that we are now at S0, dST. Now, unfortunately, this probability density function F is typically not available. However, interestingly, and we will see that in the next hour, interestingly, the characteristic function, so the characteristic function, which we either denote by F hat or by phi, we will often see phi in my talks, that often is available. So we will, and a characteristic function is the Fourier transform of F. Yes, that often is available. Now, my very final slide. No, yeah, almost. So there are several pricing techniques for obtaining the information on prices of options. Preferably, we have the exact solution. It is the fastest. Think of the Black-Scholes world. There are semi-exact pricing techniques. They only hold true for a limited parameter range. It's like based on perturbation techniques. And then we have the numerical methods. And there we can think of Fourier methods, PDEs, trees, and Monte Carlo simulations. And in the next lectures, I will first do Fourier techniques. Tomorrow, I'll say something about PDEs, and Monte Carlo simulation will also come. All right. That's it for my first 50 minutes.
Okay. Please, Kees.
So I finished with these two formulations, right? The PDE formulation and the stochastic interpretation of the solution as the discounted expectation under the Q measure of the final condition. And you can imagine that both of these approaches, they have their advantages and disadvantages. And one can now apply several numerical techniques based on the formulations that originates from the Feynman-Cutch theorem. First of all, you have the discounted expectation that could be numerical integration. If we have F known, but if we do not have F, but we have the characteristic function available, then numerical integration boils down to pricing in the Fourier domain. This formulation also gives us possibility to do Monte Carlo simulation, right? An expected value is an average. An SDE can be simulated, can be discretized with Euler-Maruyama or with Milstein. And later on in this week, we will see the so-called 7-league scheme, which is a possibility. And then we can look at discounted payoffs and we can average them. And by this way, we do Monte Carlo simulation to get to the option price. And we also have the numerical solution of the PDE, or when we're dealing with integrals in the case of jump processes, we even have PIDEs, partial integral differential equations. And each of these methods has its merits and demerits. First of all, for example, we can have the problem's dimensionality. When we have a high dimensional problem, numerical integration may be difficult, numerical solution of the PDE may be difficult, and we will resort to Monte Carlo simulation. Yeah, the speed of the solution methods is may be important. And in terms of speed, it's typically the numerical integration, which is the most favorable. The Fourier space is maybe most favorable. And sometimes we have early exercise features and we are dealing with a free boundary problem, like tomorrow morning, I will talk about that. And in that case, we often see, classically, we see the numerical solution of the PDE appearing. But in my talks, I will also discuss the other two then. Now, if we go back to our setting from before with the calibration phase and the pricing of the product phase, then we see that this needs the highest speed. So here you can really think of quadrature methods, numerical integration, and Fourier techniques. And if we need to price a product of interest, this is typically a difficult product. So here you can think of the PDE approach or the Monte Carlo approach, right? So, so basically, sometimes you see these being compared, like we compare Fourier techniques with Monte Carlo, or we compare Fourier techniques with PDE techniques. My feeling is that often you need both. One of the techniques you may need to calibrate models, and the other one you may need to price high-dimensional or complicated products of interest. So today we are in the setting of 3, and tomorrow and later we are in the setting of 5, and even in the setting of 5, and even in the setting of 6, understanding and removing the risk related to counterparty default. So today we need speed. We need the highest speed. And then I mentioned that typically we don't have F available, but interestingly, we have the Fourier transform of F available, and that is called phi. Now, if you are a little bit familiar with PDE techniques, then you see some more. You see that this is in fact an integral formulation of the PDE, right? This is an integral formulation. So if you wish, this is a parabolic PDE, right? It's a parabolic PDE. And what we have here is something like a Green's function formulation, yeah, a fundamental solution formulation. And then this F here, the probability density function, is like a scaled Green function. And what we say now here is that often we don't have the Green's function available, but we do have its Fourier transform available. So we are working with the Fourier transform of F. And therefore we say, let's go into Fourier space and let's work there and solve it there in order to get the highest efficiency in the calibration phase, and because we have the characteristic function available. Now, the first part of this second lecture is, why do we have the characteristic function available? That is what I want to discuss today. So we will go into Fourier methods. We wish to derive pricing methods that are computationally fast because they are meant for the calibration phase. They are not only restricted to Gaussian-based models, so they should also work for jumps, although we don't discuss jumps in so much detail in this lecture series, but they should also work for jump processes. Essentially, they should work as long as we have the characteristic function available, and the characteristic function, I denote it with phi. The characteristic function is the Fourier transform of the density function. So the integral from -infinity to infinity, e to the I ux fx dx. And this Fourier transform, this characteristic function, it is available for Lévy processes by means of the famous Lévy-Kinshine theorem, but it's also available for the Heston model for diffusion processes for affine jump diffusions. And again, in probability theory, a characteristic function of a continuous random variable is equal to the Fourier transform of the density of X. Now, why do we have that characteristic function so often available? I want to show that by means, I want to work out an example, how we get to that, and then I'll come with a well-known theorem from about 20 years ago, the Duffy, Pan, and Singleton theorem, that tells us when we have the characteristic function available. So the question is again, why do we have the Fourier transform of the density, but not the density itself in closed form often. Now let's go to the Black-Scholes case. Yeah, I will do the derivation in detail and then I come up with the theorem. So we are again in the Black-Scholes setting, the Black-Scholes equation, and let's do the substitution. X is log S. Yeah, S is the stock price and X is log S. And let's look at the impact on the PDE. Right? So then we have a new unknown, capital U, and it depends on X and T. And that is, well, equal to V, which depends on S and T. So we need to do the transformation. We do the chain rule if we need it. dV dt is equal to du dt. dV ds is equal to du dx dx ds. And dx ds in this setting, dx ds is 1 over s. So dV ds is replaced by 1 over s du dx. And the second derivative of v with respect to s is, in fact, we take the dds of this term, it's minus 1 over s squared du dx plus 1 over s squared, the second derivative of u with respect to x. Substituting all this in the Black-Scholes equation, moreover, looking at time forward in time, so tau is time to maturity, capital T minus small t, which gives us a minus sign here. Then we end up with this PDE. You may have seen that also in an earlier course, minus du dt d tau plus r minus 1/2 sigma squared du dx plus 1/2 sigma squared, the second derivative of u with respect to x, minus ru is equal to 0. And this is a PDE with constant coefficients. So there's no S term in front or X or anything. These are constant coefficients. It's a second order parabolic PDE with constant coefficients. And for those, we know the solution, right? For those, we can probe a solution. Yeah, we probe the solution. Let's assume that U, our solution, and we call it phi. Let's assume that is e to the power a function a of u and tau plus b of u and tau times x. Yeah, so a PDE, a parabolic PDE with constant coefficients, we can probe this solution. Yeah. Moreover, I will explain you later, we have a boundary, an initial condition for tau equals 0, an initial condition, which is e to the power iux. But that comes later. Let's first probe this solution. Yeah, we assume that our solution to the parabolic PDE with constant coefficients is e to the power a plus b times x. Then the derivative with respect to tau is the function itself, phi times chain rule dA d tau plus x dB d tau. The derivative with respect to x is appearing here. So that is again the function itself, phi times b. And the second derivative with respect to x, that is again the differentiation with respect to x. So it's phi times b squared. Yeah. Now let's substitute all of them in the new equation. So d phi d tau, d phi dx, and the second derivative of phi with respect to x squared. And if we substitute them, we end up with this PDE minus phi, so the solution times dA d tau plus x dB d tau plus r minus 1/2 sigma square phi times b plus 1/2 sigma square phi times b square minus r times phi is equal to 0. That is the solution that needs to hold true when this phi, this probed solution satisfies our PDE. And because it's a PDE, then here you see that we can, in fact, we can take straight D's, right? We only have derivative with respect to tau. So we can say these are straight b, db, d tau, and dA, d tau with straight d's, because we only have derivatives with respect to tau. Now, how can we solve this? That is known. So we can solve this by saying that all the terms with respect to x need to be equal to 0, and all the terms that are not related to x need to be equal to 0. Well, first of all, you see that phi itself cancels out everywhere, right? We can divide by phi. And then what remains is one term related to the x term, that is dB, d tau is equal to 0. That should then be equal to 0. And all the other terms should be equal to 0. Then we satisfy this equation. So dA, d tau plus r is equal to r minus 1/2 sigma squared times b plus 1/2 sigma squared b squared minus r. Those two equations need to hold. And they are related to the exponent here, the function a and the function b in this general solution are given by these two equations. And we have an initial condition which is related to the characteristic function. We say that phi at tau equals 0 should be e to the power iux. E to the power iux. So that is only related to the x term in the exponent, in fact. All right, we have dB d tau is equal to 0. So b is equal to a constant, right? And that constant is then given by that initial condition. So let's first do that. And that gives us the constant from the constant is I times u. Yeah. So for b, the initial value at tau equals 0 is I times u, right? B at tau 0 is I times u. And that gives us the constant b of u and tau is generally I times u. And the second one, so with I times u, we can substitute I times u here for b and for b square. Of course, I times u times I times u is minus u squared, right? So we substitute that, and here we have I times u. dA dt, dA d tau is a constant, r minus 1/2 sigma square I times u plus 1/2 sigma square times minus u square minus r. And the solution is then that times tau, right? So the solution for A is r minus 1/2 sigma square iu tau minus 1/2 sigma square u square tau minus r tau. And then we have, because the solution for tau is 0 is equal to 0. And that is also the case. So the obtained characteristic function is given by this general expression here, e to the power a plus bx. And we have now determined a and b by means of solving these ODEs. And we call them Riccati ODEs. We solve them. We first solve one. Then we substitute the solution into the other. And then we can solve the other rather easily in this case. And we end up with phi of u and tau is e to the power r minus 1/2 sigma square times iu tau minus 1/2 sigma square u square times tau minus r times tau plus iux. And that is the characteristic function. And we have derived it in a tedious way. Now I want to go back a few slides. I want to go back to this equation, this connection between the Black-Scholes equation and the discounted expected payoff. In fact, the only place where the explicit relation to option pricing appears is here with this V. This V at final time is the put or the call in this case. However, we can choose anything there, right? In principle, we can choose anything and we can from final time, we can take it back to initial time with this PDE. And particularly, what happens if we choose for V e to the power IU, e to the power IUS, for example, or e to the power IU, let's say x, and x is a function, and that function will enter here and here as well. Well, if we look at that, if we choose for our final condition an exponential function, what we have under the integral sign is in fact a Fourier transform of f. E to the power IUX times a function which depends on x somehow is nothing but a Fourier transform. So if we solve this with final condition e to the power IUX, what we end up with is not an option value because we have a different final condition, but we have the characteristic function. Yeah, so that is the basis of this derivation, that this connection, the connection here between this formulation and this formulation is much more general than for options. In fact, this is a Kolmogorov equation, and they are known for the development in time of probability density functions, for example. And we can also use it by saying, if we use as our final condition a complex exponential with a suitable exponent, then in fact what we are doing is we are solving not an option, but we are solving this characteristic function, the Fourier transform of f. And that is what we just did. Yeah, that is what we just did. We don't have it for the full Black-Scholes case, so we need to first do a log transformation. Then we have a problem with constant coefficients. Then we probe this solution, and by placing explicitly phi at 0 being equal to e to the power IUX, we make this a characteristic function. Yeah, we make this a characteristic function. We solve this equation. We solve this equation with a specific final condition, and we do a transformation so that these S terms disappear, because then we know a probed solution. Then we know this solution. E to the A plus BX. With this specific initial condition in tau, we guarantee that we have a characteristic function. And with the Riccati ODEs, we can find the characteristic function, and we get it like this. So this is somewhat tedious to go through this all the time, but fortunately, Duffy, Pan, and Singleton have made up a theorem that tells us immediately whether or not we have a characteristic function. Suppose generally that we have a system of SDEs. It's a system, so we have bold-face X and bold-face X here, and it's a system of Brownian increments, d omega tilde. Now, suppose we have the following system. dxt is mu bar. It's a general drift function times dt. And the drift function may depend on the vector itself, on the vector of random variables. And we have plus sigma bar depending on x d omega t. And we have the independent Brownian motions. So there's no correlation here. These are the independent Brownian motions, w of omega tilde. Now, if these functions mu bar and sigma bar have a specific form, it is basically when mu bar is linear. So when mu bar consists of a naught plus a1x, and when the interest rate is linear, well, in our case, it's constant, so that's okay. And moreover, this is a matrix, sigma bar. Now, when sigma, this is a vector, but we look at the matrix sigma bar times sigma bar transpose. And when each of the elements in sigma bar transpose is linear, is C0 plus C1 times X. So when mu is linear, when sigma times sigma bar sigma bar times sigma bar transpose has linear elements in its matrix, and when the interest rate is linear, then Duffy, Pan, and Singleton have given us a theorem in 2000. They have shown that for so-called affine diffusion processes, and these conditions are related to affine processes, affine diffusion processes, we have the characteristic function available. We have the so-called discounted characteristic function available. There's a discounting term involved here. And so we have it available, and it has this, this final condition in T, e to the power iux, and in our tau from before, it is at 0, tau is equal to 0. And we know from Duffy, Pan, and Singleton that then we have a characteristic function which looks like e to the power a plus b times x. And in the vector form, it's b transpose, right? It is a vector b. And how do we find these coefficients a and b? Well, we find them by means of the so-called Riccati ODEs. So we have a Riccati ODE. Again, here you see the straight D's, dd tau of A and dd tau of B. And they are related to these coefficients in our SDE system. It's R0, B transpose A0, and half B transpose C0B, and R1, A1, and 1/2 B transpose C1B. And these R0, A0, and C0, etc., you see them appearing in the SDE system. Yeah, we see them here, A0, A1, C0, C1, R0, R1, they appear here. So in other words, if we look at the vector of SDEs, if we look at the vector of SDEs, the vector form of the SDEs for our price process, and we see that the drift terms are all linear, and we compute in the version with the independent Brownian motions, and we compute sigma bar times sigma bar transpose, and we look at each of its elements, and if they are linear, and moreover, when the interest rate process is linear, when all these conditions are satisfied, we know that we have a characteristic function. We know how to get to these, and it looks like a e to the power a plus bx. And we know how to get these a's and these b's by means of Riccati ODEs dA dt, dB, dt. Right? So we just look at this and we know already whether or not we have a characteristic function available, and we can either derive it analytically or we can get it with the help of numerical techniques. And it is generalized to even to the affine jump diffusion class. So also for jumps, where the jump intensities should satisfy certain properties, also for affine jump diffusion processes, we have a characteristic function available. Okay, so let's look again with this SDE, with this theorem in our hands, Duffy, Pan, and Singleton. Let's look again at geometric Brownian motion. ds is equal to rs dt plus sigma s d omega. Well, here we see this is r times s. That is linear, so it's affine. This mu bar term is affine. But in total, the process is not affine, because here we have sigma times s as our sigma bar function, sigma times s. And we need to take it, it's a one-dimensional matrix if you wish. So we need to take this one times its transpose, so we need to square it. And then we end up with sigma square s square. And this is clearly not affine. S square is not linear. So therefore, for the SDE, for geometric Brownian motion, we don't have the characteristic function available in closed form on the basis of this theory. We can't use this theorem. Yeah? And therefore, we need to go to log space. We need to go to log space first. X of t is log st. Then we have the Ito's lemma, of course. We have Ito's lemma. We take the function is the log. So therefore we know that d log st is equal to r minus 1/2 sigma squared dt plus sigma d omega. And here we see constant coefficient and a constant coefficient. So if we look at our drift term now, in this case, our drift term, it has a constant coefficient. It is r minus 1/2 sigma squared. That is our a0. And a1 times x is that's not there. So a1 is equal to 0. Now for this, if we look at sigma bar square, then we see that is equal to, well, you see it here. Here is sigma, and sigma is a constant here. So that is sigma squared. That's our C0. And C1 is equal to 0. And our interest rate is just constant R, and R1 is equal to 0. So now we have A0, A1, C0, C1, R0, and R1. We can substitute this into our Riccati ODEs, R0, R1, A0, A1, C0, C1. We substitute it over here. And because we are dealing with a scalar SDE, our vector valued B is just a scalar. And when we substitute it, we get our characteristic function. Again, Duffy, Pan, and Singleton then tell us our characteristic function is given as e to the power a plus b times x. And then we can find these a and b functions with the system of ODEs. The system that Duffy, Pan, and Singleton tell us is written like this: dB d tau with R0, R1, A0, A1, etc. And in our case, R1 is 0, A1 is 0, C1 is 0. So dB d tau is equal to 0. And dA d tau is, well, related to R0 minus R here. A0, it is R minus 1/2 sigma squared times B plus 1/2 sigma squared B times B. We have the final condition. We know that, and if we go in tau, we have an initial condition. For B, it's IU, and for A, it's 0. And we end up with the same as before, of course, B being I times U, and A being minus R plus IU. R minus 1/2 sigma squared minus 1/2 U squared sigma squared times tau. And again, we get to the same characteristic function, but now, of course, we don't need that tedious derivation anymore. We can just rely on the Duffy, Pan, and Singleton theorem. And then we have the characteristic function in closed form. Yeah, so we have the characteristic function in closed form. Now let's go to our Heston model, and let's see if we have a characteristic function available. So our Heston model looks like this: dst is equal to r times s dt plus the square root of v s d omega 1, or x or s, how you want to name it. dv, d nu is equal to minus kappa nu t minus nu bar dt plus gamma, the square root of nu, times d omega. Now, is this affine? That is the big question. Well, here in this space of in the drift, mu bar, we see r times s is okay, kappa times nu is okay. So in terms of the drift, this looks good. However, of course, you can imagine it does not look good in terms of the volatility term, because here we have an s, and we need to square it somehow. We need to make something like sigma bar tilde. Well, with the s here, this doesn't look good. So it doesn't look affine right now, but we are not yet in the setting of the Duffy, Pan, and Singleton theorem. First thing we do is let's do a log transform for the first one. Yeah, we need to do a log transform anyways, like we did in the Black-Scholes case. We do a log transform. So we say xt is log s. And then if we do Ito's lemma, we end up with dx t is equal to rt as r minus 1/2 nu t dx plus the square root of nu d omega 1, and d nu is equal to minus kappa nu t minus nu bar plus gamma times nu. Now the question is again, is this affine? Well, you know, this is not yet the good formulation, because we are still dealing in our original formulation, although we have done the log transform, we are still dealing with correlated Brownian motions, right? And in our theorem, if we go back a few slides, our theorem says that we should be dealing with the independent version of the Brownian motions, the independent ones. And before we have said that there was a correlation between these two Brownian motions, d omega 1, d omega 2, there was a correlation with rho. So we first need to go to the formulation with the independent Brownian motions. So let's do that. And then, so we do the independent Brownian motions. So we have dxt is r minus 1/2 nu t dt. And then here we just copy the first one. So it's the square root of nu. And the second here is 0. That is the first one. And the second one, we make it orthogonal to the first one. We call them omega tilde x and omega tilde nu. And the second one, as you may know, by making these orthogonal to each other, the second one is then rho x and v times gamma times the square root of nu t. And the second term here in that matrix here is gamma times the square root of 1 minus rho squared times nu t. And the Brownian motions, omega tilde x and omega tilde nu, they are independent of it. So now we are in the setting that we can look whether these two are affine, and when they are affine, then we know that we can get to a characteristic function for the Heston model, this forms the basis. Well, again, the drift terms, they are affine. You see, this is linear in nu. This is also linear in nu. So they are all both affine. And now this one. Well, this one, we need to, this is then our sigma bar, right? Sigma bar. And we need to multiply it with sigma transpose. And then we need to look at each of the elements and see whether they are affine. So if we do that, sigma bar times sigma bar transpose. So we transpose this, we multiply it with this one, we end up with nu t times gamma times rho. Of course, it's symmetric, nu t times gamma times rho. And here we have gamma squared times nu. And each of these terms is indeed linear. Yes, so each of these is linear, and then we can conclude that indeed the Heston model is also an affine model. And that means that we have a characteristic function available, and we can compute it with the help of the Riccati ODEs. So we are in the good setting, and that is nice. So let's continue. With this, now we have shown you two ways to get to a characteristic function, where, of course, the Duffy, Pan, and Singleton theorem for affine jump diffusions or for affine diffusions is the most convenient way to deduce that we have a characteristic function. And if we are dealing with Lévy processes, we have yet another possibility. That's the Lévy-Kinshine theorem that tells us immediately how we can get to the characteristic function. Okay, now we have a characteristic function available, which is the Fourier transform of the density. Let's discuss the cost method. Let's start with the cost method, and I will continue with that at 2 o'clock after the break. What are good features of the cost method? Well, it has exponential convergence in the number of terms. The Greeks, which are the first derivatives with respect to the option price, dv ds, and also the second derivative. The second derivative is gamma, the second derivative of v with respect to s, and also dv d sigma, the vega from before. They are essentially obtained at no additional cost. We will now discuss it for European options, but it also works for Bermudan options, for discretely monitored barrier options, and also for Asian options even. And even recently, we worked on sort of difficult options in the electricity industry. And also for those, we could make use of the cost method. And the basic idea, it's not so difficult. It's really basic. We replace the density in that discounted expected payoff formulation. We replace the density by its Fourier-cosine series expansion. And it turns out that the series coefficients will have a very simple relation with the characteristic function. So let's get started. First of all, the density and the characteristic function, fx and phi x, they form a Fourier pair. So phi, the characteristic function, is, as I mentioned before, it's the integral over r of e to the power I y u fxy dy, and vice versa. The density fxy is 1 over 2 pi, the integral of r e to the power minus I u y phi x of u du. So we can go from the characteristic function to the density and vice versa. They form a so-called Fourier pair. Now we will use Fourier cosine expansions, and in these last 10 minutes that I have, I want to refresh your memory a little bit about Fourier cosine series expansions. First of all, we know that Fourier cosine series expansions, they give an optimal approximation for functions with finite support. Yeah. So they are known to be optimal. They are connected to so-called Chebyshev interpolations. And if we think of a general Fourier expansion of a function g on -1, 1, we have all learned in the university, one of the first years of textbook, between -1 and 1, we can, any function g can be written as an infinite sum, k runs from 0 to infinity, of coefficients a hat, k, times cosine with argument k pi theta, plus a sum k runs from 1 to infinity of b bar times sine k pi theta. And here we have a prime to that sum sign, and that implies that that is a reminder that the first term in the cosine should be multiplied by 1/2. Right? This is the classical way to say a function can be, under suitable assumptions, a function can be represented by a Fourier expansion. Yeah, a Fourier expansion for any theta. We have this Fourier expansion. Again, the prime indicates that the first term in the cosine series should be weighted by 1/2. And these coefficients, a bar and b bar, they are given as follows. It's on -1, 1. So that's the integral from -1 to 1. G theta times the cosine d theta, and b is the integral from -1 to 1. G theta sine theta pi theta d theta. That is the general setting for general expansions. How do we get to cosines? Well, you know, we have all learned that cosines are basically only good for even functions. Yeah, for even functions. So let's first look at even functions. So let's first set b equals to 0. Yeah, this term cancels out, b is equal to 0. And then we obtain the so-called classical Fourier cosine expansion. And that one, the classical one, can represent even functions around theta is equal to 0 exactly. However, we can extend any function g, which runs from 0 to pi, from 0 pi to r, any function, we can make it an even function by extending it to minus pi as follows. We can say we have g bar, it is our g of theta for theta greater or equal to 0, and we make it g of minus theta for theta less than 0. Yeah, so we make any function which is defined on 0 pi, we can make it an even function by extending the interval and making a generalization. We make a continuation. So we make a g bar, which is g theta and g minus theta. Now we have an even function. The original function was odd, maybe, or different, or general. We make it an even function, and even functions can be expressed as Fourier cosine series. So let's do that. So that g bar function, which is supported on minus pi, for that we have a cosine expansion. G bar of theta is the infinite sum, k runs from 0 to infinity, of a bar times the cosine k times theta. And again, a bar, that is by definition, it's 1 over pi, the integral from minus pi to pi, g bar cosine k pi d theta. And here we have the crux. So this is an even function. And that we can solve this as this is equal to 2 over pi, the integral from 0 to pi, g theta cosine k theta d theta. So we went from g bar to g because we are in this part from 0 to pi, and there our g bar was defined as g. So g is equal to g bar on 0 pi. So therefore the Fourier cosine expansion of the not necessarily even of the general function g on 0 pi is also given by this equation above. So this way we have departed from the classical notion of even functions. We made a continuation, and by means of the continuation we do the Fourier cosine expansion, but by just a logical rewriting for even functions, saying that this integral from minus pi to pi is in fact equal to 2 times the integral from 0 to pi, we return to our general function. And therefore we can define a Fourier cosine expansion of a general function g on 0 pi. All right, now that 0 pi, that is just a scaling. Yeah. For functions supported on any finite interval, say AB, for functions supported on any, we can get also in similar way the Fourier cosine series expansions by means of a change of variables. We can just say theta is y minus a divided by b minus a times pi, and y then, if we do a little change of variables, left hand side, right hand side, etc., then we see y is equal to b minus a over pi times theta plus a. And therefore, the general Fourier cosine expansion is given as follows. G of y is the sum, k runs from 0 to infinity, of a bar times the cosine, and now with a changed argument here, k pi times y minus a divided by b minus a, and our a bar function is given by 2 over b minus a, the integral from a to b of gy cosine k pi y minus a b minus a dy. So that is the notion, that is the setting that we're in now. So we have changed from, argued from the classical Fourier cosine expansion to an expansion on minus pi of a general function which we made an even continuation of. And for that even continuation, we could look at the expansion, and we end up again with our not necessarily even function on minus pi pi. And here we just say minus pi pi is just a scaling to go from minus pi pi to a to b. And that is just by means of this. Okay. Let's look already to some extent at the connection between densities and characteristic functions. Well, one thing that is a little awkward is, of course, we know that density functions, they may run from minus infinity to plus infinity, whereas these cosine series expansions, they really need a finite domain. So they need a domain AB on which they are defined. So we need to truncate. When we're dealing with density functions, we need to truncate the domain. Yeah. So here, because of conditions for the existence of a Fourier transform, the integrands have to decay to 0 at plus or minus infinity, and we can truncate the integration range without losing significant accuracy. And if we truncate for a density, indeed, you may wonder, how does that work when we have fat tails in our density, for example? Anyway, we should know when we truncate, we should know how much mass we lose. We shouldn't lose too much mass, right? So if we have an integration range AB in R, and it's chosen such that the truncated integral at least approximate the infinite counterpart very well, that means we are looking for a truncated characteristic function, phi hat, which is now defined as the integral from a to b, e to the power iuy fy dy. And that is an approximation for the integral over R of e to the power iuy fxy dy. And this last one is by definition the characteristic function, right? That is by definition the characteristic function. And also recall that e to the power iu, so Euler's formula, e to the power iu, that is nothing but cosine u plus I sine u. And here we see a cosine appearing, and that will turn out to be very handy when we are later dealing with our cosine series expansion. So we see that the real part of e to the iu is the cosine u, and that we will be using later on. Okay, I see that it is 10:50, and I may continue with detailed derivation after the break at 2 o'clock. So I would like to stop here and ask the audience if there are any questions for my